let's continue thinking about dynamics in relativity from this geometrical perspective. Let me just show you one more example of the two pictures that we now draw. There's the world line picture, and then there's the momentum picture. Let's look at a photon bounces off a material particle, and it changes the velocity of that particle. So let's suppose the material particle is going up like this. That's A, and then here as a photon, let's see, let's call that B. And then it bounces off and goes off this direction, C, and the material particle changes its direction. Let's call that D. Okay. And so, well, let's call it A prime, because we think of it as the same particle, I guess. And maybe we call this B prime. We may or may not want to think of that as the same photon. We probably shouldn't think, well, we shouldn't think of it as the same photon, but we'll call it B prime anyway. So the momentum picture would be then PA is like this, and then PB, well, let's make sure it's really going pretty fast. Okay, so it's going to be going at a 45-degree direction, the null direction. And then, well, let's see, let's put that over here. Then PA prime is going to be like this, and then there's got to be a null vector here, PB prime, and then here's PA prime. Okay, and one thing you notice here is that the two photon momenta, the way I drew it, they happen to be not only opposite in direction but unequal in magnitude. And it's going to be important that even though all photons go at the same speed, they do not have the same energy momentum. That's really, really crucial. Okay, so that's just another example of the world line picture and the momentum picture. And you can combine these two pictures, but as I've said, when you're first starting out, it's really handy to have separate pictures, or else it gets really busy. Okay, so I just want to say a few things. If we insist on having coordinates, then we're going to take this p vector, the energy moment, what I'm calling the energy momentum vector in space-time, and we're going to decompose it into its x and t components. Well, it turns out that we're going to call the space component p and the time component e. Very suggestive. So the energy momentum vector is really going to be the space then time for our convention. And so p, now remember, I'm only working in 2 dimensions. In 4 dimensions, this would really be a 3-dimensional vector, and then this would be a scalar, or a number anyway. But I'm working in 2 dimensions for simplicity. So this is going to be the momentum I claim. I still have to justify that. And I claim this is going to be the energy. Okay, and we still have to do some work to really connect to the Newtonian notions to make sure that this really isn't just fiction. I can use the words all I like, but I need to justify it better, and I will very soon, to make sure that this really has some connection to Newtonian energy momentum. They won't exactly be the same, because this isn't the same as Newtonian physics, but that's what we're going to have. The claim is that that energy is to time as momentum is to space. And that, if that's the only thing you get out of these videos, it's a very cool thing to get out of these videos. Okay, so I want to make a few observations. One is that I could have, if I just draw the world line picture, here's a particle going through some event in some direction in space and time, basically. It could have an energy momentum vector that's like this, or like this, or like this. Different particles can have different energy momentum. And that's an experimental observation, that if something is coming towards you, you have a very different reaction depending on whether it's a feather or a bowling ball or a locomotive. Okay, they could all be coming towards you at the same relative velocity, the same world line, but you're going to be much more scared of the locomotive. Okay, so we have to accommodate that, and the obvious way to do that would be to talk about the magnitude of these different possible vectors. There's another reason to talk about the magnitude, and that is if I've got, let's just redraw this. If I've got a certain particle with a certain energy momentum vector, I can say this kind of thing that I just did, that the energy momentum vector is momentum in the space component and energy in the time component. But a different observer is going to give different momentum and energy values. So somebody else with a different coordinate system, let's put it in red, maybe their coordinate system looks like this. Remember how the t prime and x prime would look. They're going to give different components to this same vector. And so these numbers are absolutely not set in stone. And that's something that's not new in special relativity. That's true in just Galilean relativity or Newtonian physics, that if somebody thinks something has a certain momentum, well, somebody else who's moving at a different velocity relative to that object is going to disagree. In particular, if you ask the object itself, if you let the object be the observer, in other words, if you let this be the time axis, the p is always going to be 0. Now the e, that's something that we're going to have a somewhat surprising prediction about. But these numbers are, in general, definitely going to depend on how something is perceived to be moving relative to the coordinate system. So we'd love to have some number that encodes how big this vector is, that tells apart the feather and the bowling ball and the locomotive, and that different observers will agree on for the same object. Well, of course we know what that is. It's the magnitude. That's exactly what the magnitude is for, to take a vector and give you a number that measures how big it is and compares different vectors of the same direction but different magnitude, and that's something that everybody will agree on. This is an invariant. This is not something that depends on coordinates. Okay? And what this turns out to be, I'm going to make a claim that that's exactly the mass of the particle. The mass of a particle is exactly the magnitude of its energy momentum vector. Okay, and so I want to start doing some formulas now to convince you that that isn't just a fake use of the word mass, that it will actually roughly correspond to how mass, energy, and momentum, all these words, are used in Newtonian mechanics, but with very interesting modifications for high velocities. Okay, so let's say we have an observer A and coordinate system x and t for that observer. And then he's observing a particle B. Okay? And that's got a momentum P equals, if we need to actually note it, PB. And so that's going to be E and P according to this observer. According to A. Okay? Then let's actually write down what I just said in coordinates. The mass is the magnitude of the energy momentum vector, and that is, we would take the dot product of this with itself, which is, this is P comma E, sorry. My bad. Which is P squared minus E squared, but that would be negative, so I'm going to take that, and then I'm going to take the square root. Or in other words, m squared is E squared minus P squared. That is the equation you end up using over and over and over again in explicit relativistic collision problems, or any kind of collision problem. It's an incredibly important, fundamental relationship between energy, momentum, and mass. And it is really relativistic. It's not something that really is exactly like Newton, but we'll see that it does have connections to Newton. So that's our first coordinate observation, that according to A, he's going to calculate these two numbers that are very special to him and other observers would disagree on, but then he can calculate m through this equation, and other observers will agree on that calculation of the mass. In particular, what about according to B? Let's say his coordinates are x prime, t prime. Well, according to B, let's draw the picture here. Maybe I've got observer A, and then particle, and then here's his rest space. Then particle B is going through here. Okay, so this is his t and x. This is going to be t prime, and here's x prime. According to B, as I said before, the momentum is 0. So let's call that P prime, E prime. Sometimes one does the time coordinate first, and that's why it keeps getting switched up. It's going to be 0 comma E prime. Okay? So according to this guy, B itself, his own self-evaluation says, I'm not moving. The momentum is going to be 0. This vector is purely going in the t prime direction. So it's just going to be 0 comma E prime. So what does this say? Okay, they're supposed to agree on m squared, and so m squared is just e prime squared. Or in other words, somebody's evaluation of their own energy is just going to be, that's just the mass. So my estimation of what my energy is equal to m. Now, this is something that is very, very close to something that's incredibly famous, the most famous equation probably ever written down. But you don't necessarily recognize it because I've been suppressing the speed of light throughout here. Okay, this doesn't make a lot of sense if we're careful with the units and we don't set c equal to 1, because this is like kilograms and this is in joules. If we just put back the units, put back the c in so as to make the units right, and I could do a careful derivation of that, but I'm just going to do it the physicist way. Just put in whatever makes the units work. If we actually let c not equal to 1, the way they get the units right is that E is mc squared. Okay. So what does this mean? Well, we're not really sure what it means yet, because we haven't really been sure that E is really an honest-to-God measure of energy yet. And we're not even sure that m is really an honest-to-God measure of mass yet. So it's a little premature to say, oh my God, we've discovered E equals mc squared. But this is the first place it appears. The really interesting thing is that relativity is saying that if we believe that this is a good measure of energy, that it's not equal to 0 for an object that isn't moving. Because the interesting thing here is that B doesn't consider himself to be moving. And we already know that that means the momentum is definitely 0, because it's a space component, and this vector is not along the space direction, according to B. But a Newtonian observer would say, well, you know, I think energy should mean kinetic energy, and the kinetic energy of something that's not moving should be 0. Why is this not equal to 0? And that is a very interesting and very significant prediction of relativity. And when we'll come back to once we get a few more equations written down, we'll come back to an explicit collision problem and really talk about what is the consequence of this. That'll probably be in the next video. Okay, but let's continue with some more equations. We've got E equals mc squared, but we don't necessarily believe that it means what we think it might mean. We really need to figure it out better. Okay, so now let's go back. Let's go back to A's coordinates, x and t. Okay, and let's. I shouldn't have erased this picture. So remember, here's A, and then B. One thing that A and B can talk about is the relative velocity of B with respect to A. In this coordinate system, how fast is B moving? Okay, so once we've fixed a coordinate system and observer, velocity is totally meaningful. Okay, so what do we know? That we've got this PB vector. It's going along the world line of something with velocity v, and so that means that if I take the space component of any vector along that world line divided by the time component of this vector along that world line, okay, that's space over time. Oh yeah, that's the velocity. Okay, or in other words, P is E times V. Now again, if you're paying attention to units, this should look really weird because the units don't work out. I'm going back to C equals 1 again, and I'll put them back in, but it's just so much more elegant to leave them out whenever we can. Okay, so that's one equation. And then, of course, we still have E squared minus P squared equals M squared. Okay, and let's combine them. So we get E squared minus E squared V squared equals M squared. And I'm going to solve for E. E squared is M squared over 1 minus V squared. And so E is M over the square root of 1 minus V squared. Hey, that's that gamma factor again. Okay, so the 1 over root 1 minus V squared, the gamma factor, and we'll see it again and again, is coming into this equation. So one thing that's really important here is that I didn't mention before. One qualification you have with this m, I'm just calling it the mass of the particle. It's often called the rest mass, to emphasize that this was something, one way to measure this is basically exactly this guy. Actually ask the particle itself to be the observer according to the particle itself, that particle is at rest, calculate the energy and divide by c² to get the rest mass. But I don't really like this term too much because mass emphasizes that this is supposed to be an invariant quantity. It's supposed to be something that every observer agrees on. Rest mass really comes from an older understanding of this stuff that's happily mostly superseded, where people looked at this m and said, okay, that's the mass according to somebody who's at rest, and then the gamma m, they thought that was a relativistic modified mass. And it was, again, like Lorentz contractions, thinking that a particle actually gets heavier. Remember, gamma is always greater than or equal to 1. Thinking that a particle gets heavier when it goes faster. It's really a bad idea. It's really, really antiquated and a bad way to think about it. But some books, the book I used 20 years ago definitely did it. Mass is an invariant quantity. Okay? Every observer agrees on that. And you can call it rest mass if you want to. But really, invariant mass. What isn't invariant, what depends on the observer, is E. The E prime, that was B's measurement of his energy. It was just m, and if you want to put in the c², you can. Okay? A's measurement of the energy of B, that's E without the prime, that's a different quantity. Well, surprise, surprise, it's different. Of course it's different. People have different measurements of kinetic energy because they perceive different motion. Okay? So that's not itself surprising. The exact formula you get is a little surprising. But now we can finally start to connect with Newtonian physics. Okay? So we have E is gamma m, but let's put it back in this explicit form. It's m times 1 minus v² to the minus 1/2 power. Okay? Now I'm going to use a little bit of calculus here. I'm going to use the binomial approximation. Okay? And so what that is that 1 plus u, say, to the r is approximately, well, equals, if I want to use the whole series. We just have to pull this one fact out of calculus, the binomial series. This goes back to Newton, plus ... Okay, so 1 plus u to a power r, and this is most useful when u is a small quantity, is 1 plus ru plus, this is essentially r choose 2, but r doesn't have to be an integer, times u² plus, the next thing is r choose 3, u³, etc. Okay, but we only need this part, really. Okay, and so let's apply this here. So E, and I'm just going to look at the first few and get the approximation. So E is going to be m times, okay, 1, and then a minus 1/2 times a minus v². So I get a plus 1/2 v². And then plus, this is minus 1/2 times minus 3/2 over 2. So it's going to be a plus 3/8, and then a minus v² quantity squared. So you get 3/8 v to the 4th plus ... Okay? And so here's an expression, and this is not going to be useful when v is a large number, but it is useful when v is small. And remember, the v is really going to be a v over c. I'll put in the c's in a minute. If we want to actually express it with units, you have to take the v in meters per second and divide it by c in order to have the effect of setting c equal to 1. So you get m plus 1/2 mv². That's interesting. Plus 3/8 mv to the 4th. That's unfamiliar, but interesting nonetheless. Okay. So here's what it works. To make all the units work, any m has to be multiplied by c² to get the units right. There's that equals mc² coming out again. Okay. But now we're not just going to get that because according to observer A, B is moving. And we're going to get the effect of motion as well. Here it's kind of nice. You put in an mc², but then a v gets replaced by v² over c², and it just stays the same. It already has the right units. And then something that's not particularly familiar is mv to the 4th over c², which is the only thing it can be to get the units right. Okay. So here's what we've got now. That E is going to be an E0, a rest energy, which is the mc² that we saw already, plus, let's say K, which is one letter people use sometimes for kinetic energy. The Newtonian kinetic energy, this should be familiar. Hey, 1/2 mv². Okay, this is something that all those Newtonian experiments we did in Physics 1 class verified seem to be an important quantity. And this is finally where we can say, hey, thinking of this magnitude of the energy momentum 4 vector, or just space-time vector, as the mass, finally there's some connection that makes that really reasonable. Plus, okay, and then there's a correction term of a fourth order in v over c. Okay, and so that we're not going to see that hardly at all if v over c is a small quantity. And if, for terrestrial things, for billiard balls and even trains and planes, v over c is on the order of much less than 1 over 1,000. You take that to the 4th power, and you're just going to get an extremely small thing. And then even plus higher order corrections. Okay, so almost time to finish up this somewhat long video. So this is finally where we get a connection with Newtonian physics and some realization that yes, maybe the E deserves to be called energy, and maybe the M deserves to be called mass. If the velocities are low, we're never going to see this. And so, okay, it's almost saying that the thing we've been calling energy is really just the Newtonian kinetic energy. Except, wait a minute, it's plus this guy. How come we never noticed that? How come Newton never noticed this huge thing, mc squared, right here? Remember that when you use energy methods in Newtonian mechanics, or basically mechanics in general, all you really care about is differences in energy. It's a very familiar thing that you can add a constant to all energies in a calculation and never notice. It's really about differences in energy. And if this is just an unchanging constant, you're never going to notice. When would you notice? What if the E naught, which is the mc squared, what if this changes from the before and after of a collision? Okay. What if you have some process that takes a particle and the mass changes between the initial configuration and the final configuration? Then that's going to have a major impact. That this is going to change, and therefore if the total energy is conserved, which is the fundamental principle here, then you're going to get a very big contribution to the kinetic energy. And we're going to do explicit examples of that. But basically that says that if you can change your mass, you can convert that to energy. And if you have a lot of energy, you might be able to convert it to new mass. And that happens all the time in particle physics, nuclear physics, what makes nuclear energy work, that kind of thing. Okay, good place to stop, even though there's more we can say later.